All right, hey everyone, this is Mr. Kramer. So this should be the first video for week 2 for physics. This is mostly just going to be me going over electromagnetic waves. If you had me or if you were in honors chemistry last year, we actually already talked about this a little bit. But might as well do it again just for review. So I'm going to be going through some slides that Mr. Berguffin put together, and I'll post these so you can look at them later without having to watch the video if you want to. This week in general, we're going to talk about the electromagnetic spectrum at first, and that's going to help us then talk about diffraction, which is sort of the third thing light does when it hits stuff, which aside from reflecting and refracting, which we talked about last week, it can also diffract. And then if you're a chemical engineer worried about thermodynamics, it can also absorb light, but we're ignoring that for now. So, so let's get started. So waves, the electromagnetic spectrum. We all know a little bit about waves since we've talked about it. We know that there's two main kinds of waves. We got transverse waves and longitudinal waves. And we know that light and all electromagnetic waves are transverse waves versus sound waves, which are longitudinal. We learned about earthquakes, how some of them are, they both have a primary wave, which is compressional or longitudinal, and they also have a transverse wave, which is the secondary wave. So that's waves. So what we're going to really focus on today is the nature of electromagnetic waves, but then also specifically how the different types of frequencies, those different frequency ranges that characterize the different types of electromagnetic radiation that we experience, what they're used for, some properties of them, where they come from, etc. Yes. So you've seen before the electromagnetic spectrum. You've seen some image like this in your life, where there's like the long waves on one side, and they get faster, 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 faster. And we know the higher frequencies means higher energy, shorter wavelengths, and the lower frequencies are lower energy and longer wavelengths. And so lower down on the energy scale, we have radio waves, microwaves, and infrared light. On the high, super high end, we got gamma rays, X-rays, and then ultraviolet. And then right sort of in the middle is the visible light. And then within just a very narrow band of wavelengths of light is the light we can see. And as it varies from around 740 nanometers to 370 nanometers, that's the wavelength. You go from red, orange, yellow, through the rainbow, up to purple. So that is the electromagnetic spectrum. So what does that mean? What's the difference between infrared and microwave, and does it matter that infrared has a shorter wavelength than microwave? Does that mean it always has more energy or is always more dangerous? And so that's one of the things we're going to talk about. Backing up a bit, in general, just because we were talking about the index of refraction and stuff like that, the electromagnetic waves are transverse waves that travel through space, and they always travel at some modified speed of light. In a vacuum, they travel perfectly at the speed of light, which is actually now defined by, was defined by an international conference just actually last year or the year before, to be exactly like 298 million meters per second. But if it's not traveling through a vacuum, it'll travel a little bit slower than that. And that's how diffraction plays a role in separating out the visible light. So we're going to get to that cool thing later this week of seeing light bend through a prism and white light turn into the whole rainbow. Okay, so now on to the individual types of radiation and what it is that they do. So lowest energy, longest wavelengths, we got the radio waves. So they can range from a wavelength that's about this long, like a meter. So basically imagine one wavelength going through like the length of this camera shot. That could be a wavelength, that could be a radio wave, but also then imagine 100,000 meters which I don't even know what that is in normal distances, but that's also a radio wave. So giant range, basically the longer and longer and longer the wavelength of light is, it's still a radio wave. So this is the cutoff, is 1 meter. Okay, we know about radio waves. They're used for communication. The reason they're really good for communication is because A, they're low energy, so they'll never hurt you, basically. Even at high intensities, which is different from a high frequency. And on top of that, the really long wavelengths means they're really good at bending around corners. And we're going to learn about that when we talk about diffraction later this week. So because of that, it's really easy to send out one signal and then have it bend around corners and stuff and get into your home, to your antenna, etc. Also, having a resonant frequency of about 1 meter or so, that's good for large antennas. So they have a resonant frequency within the length of the antenna. I could talk about radios forever, but you know, we're moving on. All right, microwaves. So obviously we use microwaves on our own for heating up stuff, but did you know that almost all telephone communication is through microwaves? So this is good because it's also low energy, so it doesn't cause damage to people. In fact, there's sort of this cancer question mark here thing. It is more likely than not that microwaves can't cause cancer unless it's under a very large intensity. And also closer to the infrared category than not. Microwaves are actually lower energy than infrared light, which is just normal old heat, though some people kind of get that mixed up and they think that microwaves are stronger than infrared light because they use it to heat up things quickly in a microwave, but actually that's just a high intensity microwave that is causing it to heat up. And there's reasons for why microwaves work the way they do, but we'll talk about that another day. So you can get burned by microwaves because they do a really good job of specifically heating up water molecules. Water molecules have a particular bond energy. This is a chemist talking now, so sorry. A particular bond energy that gets excited by the frequency that is used in your normal microwave. However, it's not going to break down or cause heating in anything that doesn't have that threshold energy that is similar to the bond energy in water, which is why you can safely microwave your food without breaking down the proteins and sugars and stuff that make the food what it is. So it's actually really useful in that regard. Okay, next, infrared light. This is heat. Everything that is hot is communicating its energy through infrared light. You glow red, which is why infrared cameras can see you. Obviously, you can get burned by infrared light, and not just like kind of burned. You can get really burned by something that's quite hot and giving off a lot of infrared light. And that ranges all the way up to visible light. Now, you might not think of visible light as heat because you're like, well, that doesn't quite make sense. However, if I shined a very high intensity visible light on you, it would transmit even more energy than an infrared light. So even though you might not get heated up in the sense that you're, absorbing thermal energy, there is still a lot of energy that's being absorbed by bonds on the surface of your skin, and you can actually, there are some damages that are dealt by visible light. If you've ever heard of like cataracts, that is really the responsibility of ultraviolet light hitting our eyes, but also visible light plays a role in that. There's actually a condition called glass blower's eye, which is low or high intensity red and orange light that glass blowers who work with hot glassware all the time, I assume also people who work with like hot metals that glow, actually ends up damaging their eyes and giving them problems to their vision in their retina. This is actually a very narrow band of light. Very, very narrow. This is only from basically like 4 to 8 times 10 to the 14th hertz. Compare that to like infrared light, which is like from 10 to the 11th all the way up to 10 to the 14th. So a span of like 1,000. Whereas visible light only doubles. So doubling versus times 1,000, very big range. So visible light is a very narrow band. And then there's a little note here just noting that The sun is mostly in the visible light range, which is why, and also it's what gets through our atmosphere best, which is why we've evolved to use visible light to see, and why it's such a narrow band, because we've evolved sensitivity specifically to the light that the sun gives off. If the sun gave off much more light at a lower frequency, we would have renamed these categories to name visible light as the light that we could see if we evolved in that condition. So really the definition of visible light is totally arbitrary, except for the fact that we as human beings can see visible light. And so that's why we've named it what it is. But it is actually arbitrary. For example, some bees can see higher frequencies than we can. So their visible light, if bees became sentient and were the ones coming up with the definitions of everything, they would call visible light that have a different range. So instead of being here, it'd be shifted over a little bit to a higher energy because they can see higher energy light with their eyes. Now, you know all about ultraviolet light. It's given by the sun, which is a problem because it gives you a sunburn. But it's used for a lot of other things. Some objects will essentially illuminate or there's a word for this, but essentially they'll glow if they're shown under a UV light. So you've seen that with counterfeiting coins, or even just sometimes like pieces of clothing that will glow weird in a black light. A black light is just another name for an ultraviolet light. Yes. I think that's all I wanted to say. In general, stay out of the sun. It's dangerous. Tanning is really bad. Basically, you shouldn't go to a tanning salon unless you want long-term damage to your skin and potentially skin cancer. Okay, moving on. So now we're getting towards really high energy. Again, these waves are fundamentally identical to each other. So there's no difference between a radio wave and an X-ray or gamma ray or visible light. It's all exactly the same thing, just at a higher frequency, which gives it more energy, which changes the way it interacts with matter, essentially. Okay, X-rays. So very high frequencies, very short wavelengths, very, very, very short wavelengths. Earlier radio waves, we were talking about how they could be, visible. The wavelengths would be like this long. This wavelength is smaller than a nanometer, way smaller than a nanometer. So very, very, very compact waves. X-rays, of course, are used because they penetrate through all of our fleshy flesh, but they get stopped by, I'm sure it's the calcium or whatever in our bones. And so for that reason, it's used to view internal organs, obviously your bone structure, and then some organs are denser than others, and so you can see an outline of those organs just by sort of the relative penetration of the X-rays. Obviously, it's really dangerous because the high energy means they can damage cell tissue and DNA and RNA, and so that causes cancer. So that's a problem. So when it's used in medical imagery, you've maybe worn one of those like lead bibs if you've gone to a dentist or a doctor that's doing an X-ray of your body, so that you have a piece of lead protecting your thorax. Not your thorax. We're not insects. I mean, I'm an insect, but yeah, your whatever this is, your abdomen. Yes, X-rays are normally also done in very short bursts to reduce long-term exposure in hopes that also prevents some of the dangerous bad sides. Again, it's like, we say, oh, well, you can only get burned by like infrared light. Well, that's not true. If I shone an X-ray beam on you at a similar intensity, which is sort of like counting the number of photons that are actually hitting you. So at a similar intensity as like the light that's heating you up from like, something that's warm, yeah, you would get really hot. But we would never do that because that's very dangerous. Okay, gamma rays. So these are actually used, ironically, to treat cancer. The thought being that if I can target a gamma ray, because it is such it's very small wavelength, it's very precise. And so if I can aim it exactly at like the cancer cells that I'm trying to take out, the thought is, oh, well, maybe we can use this light to just kill all this tumor. However, general exposure to gamma rays is going to give you cancer the same way that X-rays do, just by causing damage to your cell tissue and to DNA. Really the biggest producer of gamma rays is like the sun, or just in general the universe. Like coming in, because they're so high energy, they can reach us from very far away, and so it's very dangerous. Actually, yeah. So that's gamma rays, the highest energy waves. Don't mess with that. It seems very scary. Okay. So here, sort of, this is a categorization of electromagnetic waves as ionizing versus non-ionizing. If you remember anything about chemistry, you know that, well, if atoms absorb enough energy, then some of those electrons can fly off as free electrons, which causes an ionization of the atom that's left behind. And so these don't have enough, these low energy waves, so radio, microwave, infrared, visible, none of those really have enough energy to cause that phenomenon to happen. It doesn't matter how many photons are smacking you, they're never going to cause this ionization. And so for that reason, radio waves, microwaves, whatever, at any intensity are going to be safe in terms of their ability to cause direct damage to cell tissue. Now, of course, if I shoot you with a ton of infrared light, you'll heat up. And, you can't just get hotter forever. You'll start burning and dying in other ways. But you're safe in terms of just overall exposure, no cancer causing, et cetera, et cetera. Okay. However, the higher energy waves, they have enough energy that they can actually cause atoms or molecules that are otherwise stable to lose electrons as those beams come in and excite those electrons and they fly off. And that causes a change in structure to those molecules. And if those molecules happen to be your DNA or proteins, that's a big problem. And so that's why these high energy radiations are very dangerous. Okay, I think we got there. So we talked about electromagnetic waves. They're always transverse waves, and they're all very similar to each other. They vary only in frequency and therefore in energy. And we talked about each of them sort of a little bit individually. So this is me, Mr. Kramer, waxing poetic about the electromagnetic spectrum. Now that you know about it and you know what they're good for, you should be able to answer the quiz that I put out. And then, then you can move on to the diffraction exercise, which is really cool. And also you'll learn some more about angles and prisms and bending light and all that jazz. So have a good one.